Hi, in this video, I will be demonstrating to you how can we apply the concept of matrices in cryptography. One question that may arise is that when we perform matrix multiplication, can we get at least one of the original matrix? To illustrate this case, let's consider example 3.17. Suppose we have two matrices, A and B, which elements are defined here, and we are asked to multiply these matrices, which gives us the matrix C, which is equal to this matrix. Is there a way that we can get matrix A from matrix C? To answer this question, we must go back to the definition of the inverse of a matrix. Recall that the product of a matrix and its inverse is the identity matrix. Hence, if we want to get matrix A from matrix C, we must know the matrix B and get its inverse. Then multiply matrix C and the inverse of B to get matrix A. Recall that C is equal to A times B. By multiplying both sides of the equation by the inverse of B, we get C times inverse of B, A times B times the inverse of B. And by the definition of the inverse of a matrix, B times B inverse is equal to the identity matrix of order n. Hence, we can substitute this to the identity matrix, giving us C times the inverse of B is equal to A times the identity matrix of order n. Finally, if we multiply any matrix by an identity matrix, we get the same matrix. Thus, C times inverse of B is equal to A. This proves our case. If we multiply the product of matrix A and B, which is C, by the inverse of B, then we get matrix A. To illustrate this, the inverse of matrix B is given here. To prove the case, let's multiply matrix C and the inverse of B. So we have this as our solution. Recall that we can rearrange the operation from this to this according to this theorem. If we multiply these two matrices, the result is this. Finally, performing this operation, we get matrix A. So what is the implication of this? We can use this to create secret messages only linear algebra students can decode. To illustrate this case, let's have this assignment of numbers to letters. Suppose further that you want to send a secret message to someone, say, "Get good mate." With this, the statement can be rewritten as this set of numbers. Using this set of numbers, we can create a 3x4 matrix and we will name it as matrix A, whose elements are the set of numbers that we have here, arranged in this order. So from row 1, row 2, 3, and 4. We may also consider a 4x3 matrix or any matrix. It doesn't matter. The important thing here is we have a matrix. Next, we create a random 3x3 invertible matrix, and we will name it matrix B, which can be called as the public key. You may choose a random 3x3 matrix for as long as it is invertible and can be multiplied to your first matrix. I'll set matrix B as this. To encode the matrix, we multiply matrix A and B, which gives us the matrix C. We will call this as the encrypted matrix. To decode this message, you need to give the encrypted matrix C and the public matrix B to the receiver. Without matrix B, it would be close to impossible to decode the message. The receiver needs to get the inverse of the matrix B, or you may provide this instead, and multiply matrix C and the inverse of B. For the sake of demonstration, the inverse of B is this. Multiplying C and the inverse of B will give us the following expression. We have the matrix C, 156, 34, 121, 105, 21, 56, 80, 21, 62, 87, 759 times 1 over 17, negative 2, 2, 3, 5, negative 22, 1, 4, 13, and negative 6. We can rearrange the order of the operation. We can have this as our first multiplicand. For the second multiplicand, we can have the matrix C. Then we can have the inverse. We perform this operation. So we copy 1 over 17. And the product of these two matrices is 119, 0, 68, 17, 153, 119, 0, 340, 340, 357, 221, and 85. Finally, performing this operation will give us the matrix A. Then, we replace the numbers with the letters. So 7 is G, 9 is I, 20 is T, 0 is a space, 7 is G, 21 is U, 4 is D, 0 is a space, 13 is M, 1 is A, 20 is T, and 5 is E. And there you have it. You were able to send a secret message using matrices. Thank you for watching and have a good day.